All right. Next concept we want to talk about is the concept of GCD and LCM. Okay. So the full form for GCD is greatest common divisor. Right. So what is the meaning of the greatest common divisor? Again, you want to start with integers which are not zero. Yeah. And then the largest integer D, such that D divides A and D divides B, is called the greatest common divisor of A and B. Okay. So this is a definition. Right. So this is a definition of greatest common divisor. For example, let's look at 24 and 36. Question is, what is GCD of this guy? Yeah. So what you do is you say, okay, let's look at the divisors of 24 and let's look at divisor of 36. So divisors of 24 is 1, 2, 3, 4, 6, 12, 24. Yeah. And divisors of 36 is 1, 2, 3, 4, 6. Does 8 goes in 36? No, 4 nines are 36. So no, 9. Then we have what? 9. Then we have 12 times 3. And then the next one is what? 36. So these are the divisors of 36. And the other one is divisor of 24. All right. So now, let's look at the following. So we have a bunch of divisors which are common divisors. So 1 is a common divisor, 2 is a common divisor, 3 is a common divisor, 4 is common, 6 is common, and 12 is common. Okay. So among them, so what is the largest of divisor which is common? 12. So therefore, GCD of this is 12. All right. So this is the idea behind GCD of two numbers. All right. Now, before I go to LCM, I want to argue that this is a very bad method. Imagine you have to find out all the divisors of a number and then look at what is common and then look what is the maximum among common. This is going to be a very bad algorithm, right? So the question is there a better way of doing this? Yeah. And the answer is yes. Yeah. The answer relies on fundamental theorem of arithmetic again. So let's talk about it. And then I'll come back to LCM as well. So the way it works is, let me just work out the example and then we can talk about it. So 24 is 2 to the power 2, which is 4, and then we have 2 to the power 3 times 3. That is 24, right? Similarly, we want to write down 36 also as what? As factors of powers of, so as you want to write 36 as product of powers of prime, okay? So what is the best way to do this? The best way to do this is having so-called factorization tree. So what do you do in factorization tree? You take 36, and can you tell me two factors of 36 which you already know? Any two factors, doesn't matter which one. 4 and 9, all right? Now you check, is 4 having, what are the factors of 4? 2 and 2. What are the factors of 9? 3 and 3. Okay? And then you look at the leaf level. You have leaf level is 2, 2, 3, 3. So you will have 2 to the power, how many powers of 2? And 3 to the power. So this is how we can basically do the factorization. This leads to a quick prime factorization. All right. It doesn't matter what, it's like this so-called concept is based on so-called greedy algorithm, if you're seeing. The greedy algorithm, basically what it does is whatever is in front of it, it does whatever it can do. And then basically this branches out and then you basically get to the answer. So take any number, yeah? Let's take, can you go say slightly bigger? Any 3-digit number, for example? 236, all right? So we see and ask what are the prime factors of it, okay? So a priori, it's not very clear to me. So in that case, my branching will go like this, right? I have 1, 36 half is what? Right? And then I see, okay, well, can I see any other quick factorization here? Well, I don't really right away, right? I can see, well, does it goes in 4? And that's one question to ask. But it doesn't goes in 3. I don't know whether it goes in 4 or not. So I'll just basically, go the same lame method of basically breaking it again. So that's gonna be what? So what is the half of this again? Sorry, half of 6, so 59, right? Yeah. And then you basically argue 59, 59, is it a prime? Looks like it's a prime, right? You basically go all the way till square root of 59, which is square root of 8, roughly, right? Or roughly you need to go until 7. So check, does 7, 59? No. 3 doesn't goes because when I add the numbers, it doesn't goes in 3. Doesn't goes in 5, I'm done. So this is the prime factorization of 236. It's going to be 2 times, so 2 to the power 2 times 559, okay, to the power 1. All right. So this is what it means by writing the factorization in terms of prime power. Okay. Now, what is the GCD? So GCD of 24 and 36. So when you want to do this, what you do is you look at the powers of 2 and what is the smallest power of 2 which is there in both of them? 2. So it's going to be 2 to the power 2. Yeah. Note that smallest power of 2, that means which is 2 square. 2 square is dividing both of them. That's why we take the smallest power, not the largest power. If I take largest power 2 to the power 3, suppose, then 2 to the power 3 does not divide the second one. So how can it be a common divisor? You see what I mean? Yeah. Similarly, let's look at power of 3. So what is the smallest power of 3? 1. So 2 to the power 2 times 3 to the power 1. Yeah. So this is going to be my GCD, which as you can see is 4 times 3, which is 12 indeed. Yeah. So this is the way to basically find out the GCD quickly and a very organized way. Yeah. Or a student of computer science would try to see, oh, what is the complexity of running such an algorithm? If you are interested, then you'll say, oh, I don't know how the number factorizes. There are some heuristics on factorization as well, right? So heuristic algorithms are the algorithm. Again, this is not related to the course, but heuristic algorithms are the algorithms which actually tell you, on average, these are the many steps it takes, or these is the factorization. This is the size of factorization, blah, blah, blah. Okay? If you're interested in how people, so there are people who study these things, right? Anyway, so this is how we find GCD, all right? So what you do is, again, let me give you another example. What is the GCD of, suppose I have two numbers. Suppose A is this. I have a number A, is 2 to the power 3, 5 to the power 1, 7 to the power 2. And I have B, which is say 2 to the power 3, 5 to the power 1. Now, what is GCD of A and B? Again, what you do is you look at the highest power of 2, common to both of them is what? Sorry, the lowest power of 2, right? In both of them is 2 to the power. So 2 to the power 3, 5 to the power 1. And what about 7? There's no 7 in the other one, right? So you'll say, oh, what do I do then? Well, if you really want to apply this algorithm, here all the primes show up, right? You see, A is P1 to the power A1, P to the power A2, Pn to the power An. And B also, those primes show up, right? But you say, oh, here the 7 did not show up. Well, you can write 7 to the power what? 0. And that solves your problem. So you get what? 7 to the power 0, which is indeed 1. So 7 is not going to participate in the GCD. Is that making sense? Yeah. All right. So this is how you compute GCD. All right. Now, next one is the concept of LCM. So what is LCM? So LCM, as the name says, is the least common multiple. Let's take two numbers and try to find the LCMs. Okay. Let's take basically say 9. So we are interested in LCM of 9 and 12. Okay. Suppose. Yeah. So again, let's do a painful way so that we realize the beauty of the other way. All right. Yeah. So what is a 9? So what are the multiples of 9? Well, multiples of 9 is 9, right? So multiples of 9. Multiples of 9. We have what? 9 ones are 9, 9 twos are 18, 9 36, 9 fours are, no, sorry, the 27, 9 3 that 27, 9 fours are 36, 9 fives are 45, 9 6 are 54, and so on. You can keep on going. Let's just look at 12 as well, multiples of 12. We get 12 ones are 12, 12 twos are 24, 6, 48, 60. Here also, so let's go further. So we have 36, 48. I'll go further in the product of 9. So 9, what? 9, 54. What is the next one? So 9, 6 are 9, 7s are 63, 9, 8s are 72. I'll go here further as well. So I get 70. Okay. Now, the reason why I went a little bit further and was because, first of all, when I'm looking at the factors of, looking at multiples of 9, I don't even know where to stop. Do you agree? Yeah, that's one painful point. Yeah, I can go as much as I want, then I go as much as in 12. Yeah, think about it. This is done algorithmically. So algorithmically, I don't know what is the bound. Where do I stop? Right, that's one point. Actually, you can stop until 9 times 12. That's another story. So here we have bunch of multiples which are common. Yeah, and as you can see, the lowest common multiple is what? 6. So this is going to be 36. Right? But again, this algorithm is a really bad algorithm. What is a better algorithm is using powers of primes. So first of all, we break it as powers of prime. So I'm going to compute LCM of these numbers because we already have the prime factorization of them. So in LCM, what you do is you look at maximum of the power. Yeah. So what is the maximum of these two powers? Power 2 to the power 2 and 2 to the power 3. So maximum power is what? 3. Yeah. What about here? What is the maximum of these two powers? 1. 3 to the power 2. So this is what the LCM of these two guys is going to be. Yeah. Now, how do I logically come to this conclusion? Now think about it. It's a common multiple of, so I'm looking at LCM of 24 and 36. Yeah. So it's a multiple of 24. Yeah. So whatever power of 2 divides 24 must also divide what? This LCM, isn't it? Because it's a multiple of 24. Yeah. That means 24 is dividing this LCM. Yeah. So whatever highest power of 2 will divide 24 must divide this LCM. Whatever power of 2 divides 36 should also divide this LCM. That means the maximum of their powers will divide the LCM. That is the logic behind this. Why we have max for the LCM and min for the GCD. Okay. Let's look at this example again. Where did we go? With a bunch of powers here. So we have A is 2 to the power 3, 5 to the power 1, 7 squared. B is 2 to the power 3, B 5 to the power 1, 7 to the power 0. What is LCM of these two guys? Again, we look for the highest power. So what is the highest power of 2 in this case? So 2 to the power 3. What is the highest power of 5? What is the highest power of 7? So if the prime is missing, yeah, you write that prime, but with what power? 0. And so you get LCM of these A and B is going to be 2 to the power 3, 5 to the power 1, 7 squared. Okay. So this is the LCM and this is the one. So far good. Now, another nice theorem is that, again, this is from algorithmic perspective. You take a number, A and B, you compute their GCD, yeah, by looking at what? The min, whatever. Then for LCM, you don't need to go and look at the powers anymore. You can just say, use the following result if you want, that AB is GCD of AB times LCM of AB. Yeah. How do we see this result? Well, think about it. If I multiply AB, let's multiply AB, okay? So we'll get what? P1 to the power A1, P1 to the power B1, all the way to P1 to the power AN, Pn to the power Bn. Yeah, you agree? I just combine all the primes together just to see. Is that okay? Now, let's look at GCD. GCD is going to be P1 to the power, say, min of A1, P1, and then dot, 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 other things. We don't care about that. I'm just going to discuss this with one prime only, and the rest result is same. And LCM is going to be P1 to the power max of A1, B1. We agree? Yeah. So if A1 is max, or sorry, if A1 is min, it will show in GCD. And then in that case, B1 will show in the LCM. So you will see P1 to the power A1, P1 to the power P1 showing up in the product. Does that make sense? Yeah. Yeah. So you just show it for one prime and then rest is all same. You can say rest follows the same structure. So you have proven that if you multiply LCM and GCD, you get back the product of two. Okay. Any questions or comments here so far? Anyone? Now comes the very interesting concept, the concept of modular arithmetic. So what is the modular arithmetic? So again, please pay attention to the definition. Okay. Now, let A to be a number, A be a integer, and M be a positive integer. Okay. Let's take an example. Say 1, 1, 2, and let's say we have 3. And we want to basically have meaning for this number. What is 112 mod 3? Okay. What is the meaning of this mod? So 112 mod 3, it says what? A mod M. What is the meaning of this? It is the remainder when you divide A by M. Whatever is the remainder is what? Is basically 112 mod 3. So what is 112 mod 3? Anyone? What is it? Is what? Anybody said that? So you basically divide it by 3. You get what? 3 divided by, so 3 what? 3 3s are 9. And you get 22. 7s are 21. The remainder is 1. So 112 mod 3 is just. Yeah. Is that okay? Now here's the faster way of doing this. Again, we'll discuss these techniques later on. Can I do 111 plus 1 mod 3? Yeah. If I had some result, A plus B mod 3 is A mod 3 plus B mod 3, then I'm done. Why? Because 111 I intentionally chose so that I can add it to give me what? 111, when I add all the digits, I get 3. That means 111. 111 mod 3 is going to be 0. And then I have what? 1 mod 3. So this is already 0, and this is going to be 1 mod 3. But when I divide 1 by 3, sorry, yeah, 1 by 3, the remainder is still what? So you see, very quickly you can do this computation. So modular arithmetic is very powerful that way. Yeah. If somebody asks you about a remainder, you can very quickly do the remainder. Yeah, that is the idea behind. So modular arithmetic is really interesting that way. Not only that, it helps you factorize things, and there's a whole bunch of interesting application of this. So that is the first definition. What is the definition? A mod M means what is the remainder? Again, the definition should be very clear. Yeah. In mathematics, without knowing, so people say, oh, do I memorize this or that? No. In mathematics, the only thing you should have any memory of, really should have memory of, is the definition. Rest all should follow from the definition. All right. So a good mathematics student or mathematician only remembers the results, sorry, definitions, and the results are kind of, they follow naturally. after you know the definition. Okay. Now comes another definition. What is meaning of? So we talked about A. So we talked about A mod M. Yeah. All right. Now there's a definition. There's a concept of congruent modulo M. So A is congruent to B mod. Yeah. Now congruent is same as like equal. Yeah. So A is congruent or A is equal to B mod M, right? But we will use the word congruent because we are learning for the first time. So what is the meaning of A is congruent to B mod M? It simply means that A and B will leave the same remainder when you divide by M. But that's not our definition here. So we'll follow this definition. What our definition says? A is congruent to B mod M if and only if M divides A minus or B minus it doesn't matter, right? If a number divides X, then it also divides minus X. So this is a definition of the congruence. So if A is congruent to B mod M, if and only if M divides A minus B. All right. So this is a definition of congruence. It's a very powerful result. You will see that why. So for example, let's take an example. Let's take 87 is congruent to 15 mod. Do you agree with this? So 87 is congruent to 15 mod, right? Why? Well, because if I do 87 minus 15, and I did what is 87 minus 15 is 72, right? And 9 divides 72, right? So 9 divides this, since 9 divides this. All right. Yeah. And the easy way, the intuitive way to keep in mind is, what is the beauty of this? The beauty is that it will leave the same remainder. When you divide by 9, 87 will leave 6, 15 will also leave. That is what I used in my mind to calculate the problem, the example for you. Yeah. So if it leaves the same remainder, then you subtract them. What happens to the remainder? 0, right? The remainders cancel out. And that is why you get that. Yeah. So they are essentially leaving the same remainder. But the definition is what? A is congruent to B mod M if M divides A minus B. Now here comes the result. Here. So if A is congruent to B mod M and C is congruent to D mod M, then we can have that A plus C is congruent to B plus D mod M. Yeah. So let's see the proof of this. All right. Again, so let's try to pay attention to this process. So what is the process says? A is congruent to B mod M. What is the definition tells me? That means M divides what? B. That's right. So I have A is congruent, let me use the proper pen. A is congruent to B mod M implies M divides A minus B. Here I have C is congruent to D mod M. This means what? M divides C minus D. Yeah, you agree? Now you have seen this result already in previous section. If M divides C and M divides D, then M divides M plus C. Right? Does it make sense? You have already seen this. Let me just rewrite it here. You have seen this at the start of this. You can use this result now as a theorem. What does the result say? It says if A divides B and A divides C, then A divides B plus C. So this will lead what? M divides what? So we have M dividing, we have M divides minus B and M divides C minus D. This means what? M divides A minus B plus C minus D, right? Now let's do a little bit of rearrangement because I want what? I want A plus C on one side, right? And then I want B plus D on the other side. So let's do a rearrangement here. We have M divides A plus C minus C plus D. This can be rearranged to make it look like that. Oh, oh, oh. Do you agree? Yeah. Yeah, they are the same thing. Now open this up. You have A plus C minus B minus D. Also on top, you have A plus C minus B minus D. Yeah, just written in a different order. So this means what? This means if I look at this number as A and this number as B, then I'm getting what? A is congruent to B mod M, right? With the capitals, right? So same thing now I can rearrange it to make it. This implies A plus C is congruent to B plus D. Okay. So this is one way of proving it. You will say, I don't like this way. Well, in that case, you can do a painstaking way of doing it. You have M divides A minus B, right? What can you do? You can say that means there exists a K such that A minus B equals to MK. Yeah, you could have done that way as well. Do you want to see how it can go? Let's have a check. So suppose you don't want to do it this way, then I'll say, okay, what is the meaning of this statement? Let's write it here. This means what? A minus B equals to MK. And here I get what? C minus D equals to MK. Let's call it 1. Doesn't matter, right? Sometimes. Now, what do I want? I want A plus C, right? So let me bring this everything on the other side. So I have B plus K. And here I can say what? C equals to, yeah, D plus M A1. Add them. A plus C equals to what? Yeah, B plus D plus MK plus MK1. You agree? That means what? A plus C minus B plus D, because that's what we are trying to prove. That's why I'm adding it this way. Is going to be what? MK plus A1. That means what? M divides A plus C minus bracket. So this is what is the idea behind the arithmetic. Okay. Let's try to prove the next result, and then we can stop. Okay. Yeah. Then we can basically stop at this. There's a lot of fancy mathematics which is developed on top of this. There in cryptography, for example, you use from 0. So you use basically system of numbers where you go from say 1 to say 4, or sorry, 0 to 4, and then 5 becomes equal to 0. So you go mod 5, suppose. I'm giving you a very simple example. Of course, in cryptography, you use very big prime P, but in this case, we just say 5. Then what you do is you define an arithmetic on that setup. In that case, some people just drop the notation. Suppose I'm going mod 5, then 2 plus 4 is same as 1. Why? Because it is what? These two are same things mod 5. So when people do, so there are mathematics where 2 plus 4 is actually 1. Yeah, you would have already seen in your Boolean or binary, if you have done some electronics or something, 1 plus 1 is what? 0, right? 1 times 1 is 1. So you have a different number systems defined there where a lot of interesting things happen. So this is absolutely useful for future. I'll show you some papers I'm actually currently reading as well, where you can see I'll show you the arithmetic being used quite often. Okay. Anyway, let me just prove this and then we can stop. Okay. So same thing. I have AC is congruent to BD mod M. I want to prove this. How will I prove this? So, well, one way is this way here. Yeah, let's just argue this way because other way seems to be tiring for people. So you need AC, right? Multiply this out. So this means what? AC equals to what? B plus MK times D plus MK1, right? Multiply it out. What do we get? CD plus MKD plus what? MK, sorry, we already did that. B times MK1, and the last one is what? M square times K1. Yeah? Do you agree? Now, from the second part, all of them have what common in them? M common. KD plus K1B plus MK1K2. I mean, because at the end of the day, I want to show that AC minus BD is M times some integer K. I don't care what that integer is, but I want to show that it is M times K. That means what? This means what? K divides. So M divides this. This means what? AC is congruent to BD. So these two numbers are congruent. Right. And you will see later on. So right now, if you think about GCD algorithm, yeah, your GCD algorithm relies on factorizing. Yeah. Now factorizing is an intensive process. It's not easy, huh? Intensive means what?